Hello, this is Robert Talbert, and I am making this video for you to take a deep dive into the alternative grading design for one of my courses. This course was discussed very briefly in my Grading for Growth keynote presentation, but as I mentioned in that previous presentation, it's greatly abbreviated in the interests of time, and I gave just a simplified version of it. But this video is going to go deep into the weeds to see the entire process and my entire thought process of how I designed an alternative grading system for a pretty typical university course. So in the top right corner of this slide is a QR code that goes to a resource page that contains a lot of different resources from my talk, including the syllabus for the course that I'm speaking of and several other associated documents and some course assignments and assessments and so on. And I would encourage you to go get that resource page and have it in front of you so you can go even further into the weeds if you so desire. So let's begin and look at our agenda for this talk here. This is perhaps a lengthy talk. You might want to settle in because I'm going to go into great detail on everything about this course. Starting with just about the course itself, I want to talk about where I was coming from, the mental space I had when I was creating the grading system, and then breaking this down into the component parts of the grading system, how I did basic skills, how I did conceptual mastery, engagement, and how I pulled all this stuff together to determine a student's course grade, and then have a brief but frank discussion about what worked and what seriously didn't work and needs some improvement. Again, I would just remind you that the resource page for my main keynote talk has a lot of even more detailed documentation about this class. And so I would encourage you to go click that link or scan the QR code and go check it out. So first of all, let me just explain about the course itself. The course itself is called Discrete Structures for Computer Science 2. This is the second semester of a year-long class on the basic foundational storehouse of mathematical knowledge that every computer scientist needs to know. The first semester of the course deals with things like logic, set theory, counting, just a tiny bit of the concept of mathematical proof, and a few other related topics. The second semester keeps going into more topics, particularly focusing on graph theory, the theory of mathematical relations, trees, which is a fundamental data structure, and a much deeper look at mathematical proof. In fact, in the first semesters, the students are expected to learn about proofs, but in the second semester, they're expected to be writing their own proofs, which is a considerably higher level task. The class size is pretty typical for us at Grand Valley State University, about 30 students, give or take. Nearly all of these are computer science or cybersecurity majors, and usually about 2/3 to 3/4 of them are in their third or fourth year. They're quite advanced and far along. Many of them are about to graduate when they take the course. This class, interestingly, is not technically a prerequisite for anything else at the university, which has brings its own set of issues. However, the content knowledge in the course is used in several upper-level theoretical CS courses like the algorithms course or our automata class. That's actually a math class, but it's a theoretical computer science class for CS majors. Now, two of the guiding documents for this course are a syllabus of record, which is a syllabus kept on file at the university that is just sort of a generic starting point for anybody else who is teaching the class. I've got my own syllabus that you can read. The syllabus of record is where we start. And then also the organization called the Association of Computing Machinery is deeply involved in helping us determine what we should teach in that course. And I'd like to take just a moment to go into both of those documents, the syllabus of record and the ACM guidelines for the course. Here is the syllabus of record for Math 325, which is the name of this course. And I only bring this up because when I'm determining the topics and the kinds of assessments and so forth that go into the class, this is where I go first. You can see that we have a number of learning objectives about computation, solving theoretical and applied problems. There is a sort of an optional computer programming component to this, that some of us include Python programming in this course as well, and I do that just a little bit. It won't show up in the rest of this video, however. The main thing here is the topic list, and just to mention the topics, you can see, as I mentioned, graphs, relations, and trees. These are some fundamental ideas in computer science, and especially, again, the role of mathematical proof is a particular emphasis in this course. It is almost the equivalent of what a mathematics major would take when they are taking an introduction to proof class. And so that's our guiding system. They have some suggested methods of evaluation here, but mostly those are left up to the instructor's devices. Now, by contrast, here is a document produced by the Association of Computing Machinery, a professional organization that doesn't exactly govern computer science undergraduate instruction in the United States, but if you're a university doing undergraduate computer science instruction, you want to keep a close eye on this document. And as you can, this is its recommendations for discrete mathematics. Many of these topics in the CS core are actually topics from the first semester of the course. In particular, the sets, relations, and all this stuff here. We do cover recursive mathematical definitions, the modular arithmetic, logic. What is really focused on in the second semester is proof techniques and graphs, and also we include a couple other things too about trees and relations as well. But when we're deciding what specific topics to go into that course, and what learning outcomes we should have, typically I'm going back to either the syllabus of record or this list that you see in front of you here, which kind of gives me a sense of what I ought to be doing in the class. So with that, let's go back to the main slides. So when I think about the course, I have a sense of who's taking it, what role it plays relative to the rest of the curriculum in either the math program or the computer science program, and what topics should be covered and why they should be covered. And that's an appropriate starting point for course design. From that point, what I did and what I always do is think about exactly what should be taking place in this class. And I tend to think of the course goals, the learning objectives in any class that I teach along three axes, an X, Y, and Z axis. On the X axis, there are basic skills that students need to master. These basic skills differ from course to course. For example, they would be different in a calculus course than they are in my discrete math course. But in my discrete math course, there's going to be basic building block skills that students should demonstrate mastery over. On the y-axis, and sort of orthogonal to the x-axis, are the students' ability to take those basic skills and apply them to new problems. Okay, maybe those are applications of the basics that they're learning, and in our course, it might be proofs about those basic skills, those basic concepts that they're learning. Both the x and the y axes are equal importance in a class like this. And that's why I chose to deal with this class in the main keynote presentation, because even though you may not be a math or a CS instructor, I think a lot of classes are like this, whether it's philosophy or sociology or what have you. There are basic skills to master, and then there's further up the Bloom's taxonomy pyramid skills that need to be mastered as well. Learning the basics and then learning to apply them to real things, or do extensions of those skills, or write something coherent about those skills at a high level. So I think this class, even though you may not care what a graph or a tree or a relation is, if you're teaching a college level class, you might find some resonance in what I'm saying here. And then there's a z-axis that's orthogonal to both of those, and that's what I would call engagement. Engagement is a very tricky word to define or get your mind around. I think of it as participation in the community of learners. Okay, are you coming to class? Are you doing what you're supposed to do? Are you putting in the work to get ready to learn what you need to learn? Are you helping out? Are you engaging outside of class? There is a question about whether engagement should be part of a grading system at all for equity purposes. And I get that, and I'm not going to get into that, but I really want students to be engaged. And so I would like to have some measure of engagement happening in the grading system that I do. Now, having determined that the course grade ought to be some sort of representation of students' progress along all three of these axes, one thing that I like very much to do when designing a course is to sit down and ask myself, if a student got a C in this course, what would that exactly mean? Not in terms of how many assessments they got or what average they have or anything like that, but just how would I verbally describe a student who earns a C in this class? For me, in this class, and maybe this applies to many other classes, a C student is a person who's mastered all the essential basic skills and some of the others, if not all the others, and they have some non-zero evidence of ability to apply them, and they're reasonably engaged. Like, they come to class most of the time. They've done a couple of good things in terms of applying basic skills, and all the basic skills that would be important for future work have no question about them. Do I expect the student to have like incredible mastery of every single skill? Not for a C. However, for an A, the bar is higher. An A student, if a student gets an A in my class, I would like to say about that student, for example, if they're applying for graduate school or a job and I have to write a letter of recommendation for them, I would like to be able to say this student has mastered almost all of the basic skills in the class, if not all of them. They consistently show excellence in taking those basic skills and doing something higher with them, whether it's applying them to interesting application problems or extending the idea or proving something about that idea. And they are consistently engaged in the class, coming to class every day unless it's impossible, doing stuff outside of class, being a leader in the class. I noted later after I wrote this that I used the word consistent twice, and I think that's good. That's a good way to describe an A student. They're very consistently excellent across the board. And I do this because when I go to actually define the details of the grading system, the results that come out of the grading system should faithfully represent the verbal description that you see here on the screen. I do not want to end up giving an A to a student that has not mastered all the basic skills or has not shown consistent evidence of excellence in applications or is not consistently engaged. Likewise, I wouldn't want to give a C to a student who has done more than what you see there in the description of a C. So I use these verbal descriptions as like reality checks once the system is built to see if the system has construct validity. Is it actually measuring what I think it measures? Now with that, let me begin to get into some of the details of how the system actually got built. I should say before I do this that this did not come out of my head fully realized. There was a great deal of trial and error and note-taking and trying out prototypes in the summer before this class ran in fall of 2024, and a lot of it got left on the cutting room floor. But here, what you're about to see here is what actually made it into the syllabus, which again is on the resource page, and you can check that out. So when it comes to basic building block skills, the stuff that's on the x-axis, I went through the entire course. I sat down for about 2 hours with a notebook and just wrote down every skill that a student will encounter in the class. And this was a long list of skills, probably close to 70 to 80 different distinct skills that I noted in the class. Out of that list, I tried to distill it down to a much shorter list of between 12 and 16 really essential skills, like the main skills of the class that I really want to make sure they're so important that I am willing to expend time and effort to eventually assess them. When you're designing a class, there are many, many skills that a student, and concepts and processes and everything else, not just skills necessarily, that a student might encounter, but you don't necessarily intend to assess a student on those skills. Students see a lot of things, and you hope they take away more than just a short laundry list of skills, but students will see a lot of different things. Not all of them are going to rise to the level of meriting a quiz or test or essay or whatever on these things. Those are only going to be saved for the very top, maybe 10% of what students learn. For me, the top, this is probably more than 10%, probably more like 25% of what I identified, ended up in this list of 14 skills. And I just call them skills. I don't try to invent special words for them. Skills. And you can read them yourself. And these are all combinations of things that I saw in the syllabus of record, things that I saw from the ACM guidelines, partly fleshed out to specific things like Euler paths and not just graphs, and specific algorithms for determining such and such. Some of these are not in either of those documents, but it's traditional that we teach those things in the class, and I like teaching them. We had room for it, so I threw them in. And you can see these are the 14 basic building block skills that students will learn in the class. Some of these are consolidations of 2 or 3 or more of the fine-grained skills that I went through and found in my notebook. Some of them are one-to-one representations. You'll notice that 5 of these have the word core in front of them, numbers 1, 2, 3, 7, and 11. Those are the skills that happen to be on the list of the ACM requirements. And so if the ACM says it's a core skill, I'm going to say that it is also a core skill. And the core skills here have a special bearing on the student's course grade that I will get to in a few slides from now. So we have these 14 skills, and so these are the ones that level up to. I should say too that making this list of 14 skills saved me many minutes, possibly hours of time later in the semester. Because if you think about it, there's 14 skills here. There's 15 weeks in a semester, so it's pretty easy to organize your entire course calendar around these 14 skills. Just do one a week on average, and that's what we did. And it was a really great way to structure my course planning so I didn't get off track. Now, these are the skills that rose to the level of I want to eventually assess them. Assessing things means grading, and grading stuff is hard work that nobody really wants to do. So I only want to do it for the most essential skills. So how did I actually assess these 14 skills? I did it through what are called I did it through what's called skill exams, but there was an intermediate layer first. From the skills, I designed the class, like I said, around activities based on the skills. For example, when we're studying, when we're just introducing skill number 5, which is about using the greedy algorithm to find a vertex coloring for a graph and determining a graph's chromatic number, that whole week was nothing but in-class practice on, guess what? Using the greedy algorithm to get a vertex coloring and then determining the graph's chromatic number. We just did lots of practice on that throughout the week, and those are based on the skills. So the class activities are aligned with the skills. And then the assessment, what I was about to say, are what are called skill exams. And these are exams, in-class exams, hour-long exams, given every roughly 3 to 4 weeks. Every exam contains one problem per skill covered in the class so far. I'm going to say a little bit more about that later. So if we've covered 4 skills in the class so far, skills 1 through 4, the exam's going to have 4 problems on it. Later on, once we've gotten through skills 1 through 8, the exam is going to have 8 problems on it. And again, I'll clarify that in just a moment. Each problem covers only one skill, so it's very closely targeted and aligned with the skills on the list. And in fact, every problem is not only aligned with the skills, it's a direct instantiation of the verb that is in the skill. If you look at those skills, all of them use the words I can, and then it describes doing something. I can perform a particular action. Okay, I can determine whether a graph is a tree. I can execute a breadth-first search in a graph. I can calculate a graph's chromatic number. These are all concrete action verbs, not something like I know how to find a graph's chromatic number, or I understand chromatic number, or something like that. Knowing and understanding, that's kicking the can down the road, because how do I know if you know how to compute a chromatic number of a graph? Well, then I would have to ask you to do something that demonstrates the knowledge, and that action that you perform is the real skill. And so that's what's in the list. Let me show you an example here. Here is skill number 2 about outlining a proof using 3 different proof techniques. We practice this in class, and on exam 1, this was the actual problem. I give them a statement, and I ask them to set up the outline for a proof by a direct proof, a proof by contrapositive, and a proof by contradiction, which is exactly what the skill says. So there are no surprises on these exams. You know the problem is coming. It's going to directly instantiate the skill. The only thing you don't know heading into the exam is what specific proposition you're going to be asked to work with. That was the skill problem on exam 1. On exam 2, we had moved on and covered 4 new skills, skills 5, 6, 7, and 8. The exam covered skills 1 through 8, and this is what this problem on exam 2 looked like. And what you'll notice is that it's 90% the same problem. The only thing that has changed is the specific proposition that students are being asked to outline the proof of. Again, the only thing that you as a student don't know heading into the exam is what specific proposition or maybe a specific graph or specific relation or tree you're going to be asked to work with. The task is still the same. The skill is still the same every single time. Now, the way these were graded, each problem on a skill exam is graded master, proficient, or beginner. In this document, this is a screenshot from a document called Standards for Student Work in Math 325. You can view the whole document on the resource page. And in this document, it contains detailed rubrics for what's expected on your work on every kind of assignment we have. Skills and the skill problems are graded on completeness, clarity of the explanation, and correctness of the answer. And you can read for yourself what the different levels represent. Basically, to earn a master mark on a skill problem means you should pretty much have no significant errors, the answer is correct, and the explanation is clear. Anything else, you're probably going to have to redo it, and I will mention how that works in just a second. In the course grade computation, if you can call it that, looking ahead, the only mark that counts is master. Okay, you can earn a proficient or beginner on a skill problem, and that is what we call a mark that indicates progress. It tells you where you are in relation to being a master of that particular skill. Once you have attained a mastery level on a skill, even if it's on the very first try, then no more attempts are necessary throughout the rest of the semester. And that's why it's possible to keep having the skill exams grow by roughly 4 problems per attempt, is where it turns out. The second exam, for example, is going to have 8 problems on it, but if things go well the first time, you're only going to be doing 4 problems, the new ones that you've never seen before. So the exam is not graded as a whole. Each individual problem receives one of these 3 marks here. So you can take exam number 1 and get master on skills 1 and 2, a beginner on skill 3, and a proficient on skill 4. That might be how it works out. Now, these exams, here's the schedule for exams that we have for the semester. As you can see, they are cumulative. There were many different options for when these can be taken. There were makeup days built into the calendar for students who were sick that particular day. And in addition to all that, toward the end of the semester, we had some room on the calendar, and I started giving little one-off mini exams for the skills that if only half the class had mastered it, we're going to focus on that one skill for 15 minutes, for example. In all, after you count all the one-off quizzes, each skill had at least 5 to 6 attempts available to it throughout the semester. And so this is more than enough for a student to practice and get feedback and iterate through a process of getting to be very, very good at each one of these skills. So that's how basic skills were handled. Let's move on to talk about the y-axis, which is applications and higher level stuff. For the most part, the biggest assessment for higher level thinking in the class was through writing mathematical proofs. Not the only one, I'll mention that in a minute, but the main one was proof problems. I showed this slide in the main keynote here. Proof problems, there were 10 of these. You can get the list off of the resource page. There were 10 of these proof problems. Students were instructed to simply pick one that looks interesting and try to write a complete, clear, correct mathematical proof. Here, for example, is problem number 3, which is actually 3 little proofs bundled into one. They're actually from a class activity where we were working on a proof, and we had to prove these 3 things in the class proof. And I said, why don't I just put those on the list for the proof problems? And that's where that came from. Many of these proof problems were filling in details that I left out in class. As you can see, what students were instructed to do is write these up. They type them up, they save their work as PDFs and upload them to Blackboard, which is our learning management system. In Blackboard, I can mark these submissions up, make highlights, leave little comments here, and I try to be very specific and helpful in my feedback, of course, because that's one of the pillars of alternative grading is helpful feedback. And this is an example of an actual student's work where some work needed to be done, but also there was some good stuff too. So helpful feedback for me means specific and inviting. I often frame my feedback in terms of questions that I want students to follow up on. And I also try to point out the good stuff too, because it can be quite draining to get nothing but negative feedback all the time. So students would do these, they would get feedback, and then this is how they were graded. Each particular proof problem submission was graded either success or retry, depending on whether or not it met the standards that you see in front of you here. A correct mathematical proof has to be free of significant error, and the target audience is the class. Okay, so a person from the class with the same background knowledge as the author, but with no knowledge of the problem, ought to be able to follow the work from beginning to end with no extra questions and no extra work to do. This is a high standard for proof, particularly for students who have never really attempted to write a proof before. In fact, having alternative grading in place allows me to hold these really high standards for mathematical proof and not settle for less, because students can simply retry them, and that's what the retry mark is. It's a mark that indicates progress, that tells you what to do next. Speaking of that, how do you reattempt a proof problem? Students could submit up to 3 things per week. 3 submissions per week can be made on Blackboard. This could be any combination of anything. It could be 3 new first drafts of 3 different problems. First drafts of 3 different problems. It could be 3 revisions of old problems. It could be a new problem plus 2 old problems. You could submit a new problem and then turn right back around and revise it the same week and submit a revision of another, and so on. A week for us is what you normally think of as a week, starting from Sunday to Saturday. And there's no penalties for having to revise. There were no point values on these, so there's not like you get only half credit for, or 80% credit for what you turn in. There's no penalty at all on doing a revision. The only limitation is that it's only 3 times a week. And so this limitation is there to keep me sane, to keep the backlog of grading down to something doable. And especially to avoid pileups at the end of the semester if students procrastinate and don't start doing proof problems until week 14 and then want to do 10 or 8 or 9 of them all at once. It's 3 times a week is the limit. At first, I had a policy of problems having an initial deadline on them. Basically, I didn't want students to start making first attempts on a problem at the very end of the semester. For example, the very first problem had an initial deadline somewhere around the 5th week of class. And if you intended to do any work on that problem at all, you had to give me a good faith effort at a successful proof by that deadline, or else no other submissions would be allowed throughout the semester. I did this to try to prevent pile-ups from happening at the end of the semester. Eventually, I relented and just removed the initial deadlines because the median number of submissions per week was 0. Most students were not submitting anything from week to week, and so having an initial deadline was just simply not really helping. It was just causing more stress. And so I took the initial deadline off, and to the point where students had complete free reign to work on proof problems at their own pace right up until the end of the semester, as long as they didn't exceed 3 submissions a week. And so reattempts without penalty baked into the process. So that covers the X and the Y axes, at least partially. I talked about basic skills through the skill problems on exams, and I talked about proof problems. Those 2 items are what I highlighted in the main keynote. But if you watch the main keynote, you also know that I said there are some other things that I am leaving out in the interest of time and simplicity. And I want to take this to now go into those things that I left out. So now you're going to get the real full experience of what was going on in the class. So other elements of the grading system. There was an item called homework. I called it homework just because I wanted something simple to call it. Really what it was is what I used to call class prep assignments. I run a flipped classroom, which means that students get first contact with new ideas prior to class through class prep exercises. Again, I just call them homework because I figured that's a familiar handle for students, and it kind of makes them feel like they should do it. Homework involved watching video and doing some readings, and then answering a set of review questions from the previous class and preview questions about the upcoming class that were covered in the video and the readings. Class meetings pick up where the homework stops, so we don't spend time in class doing basic lecture on the basic stuff. That's what the homework is for. What we do spend time doing are practice on the skills. And so I want students to learn, for example, what an Euler circuit is, just what it is, what the definition is in the homework, and have some sense of what that is before they come into class. And then in the class, we're going to practice the skill, which is taking a graph and determining whether or not it has an Euler circuit. So ratchets up the complexity a little. I need students to cover those basic things on their own before class, and I feel like they can do it. These class preps were graded on a 2-level rubric, either success or incomplete, only on the basis of completeness, effort, and timeliness. Essentially, if you answer every question that isn't marked optional on a class prep, and some were, and you turn it in prior to the deadline, which is 11:59 p.m. Eastern Time the night before the class, you get a success mark. Anything else is called incomplete. It's called incomplete rather than retry, like my proof problems, because you can't really reattempt a homework because it's a class preparation. So all you have to do is do it, and that's what makes it work. And if you have questions as a student on anything that's covered in the homework in the class preparation, then there's a spot on the class preparation form. These are all done on Google Forms, so it's real easy to automate the collection of these. If you leave your questions on the form, and that's where I pick up when class starts, is your questions on the class prep. So these are graded success and complete on the basis of completeness, effort, and timeliness. Another element of the class was what's called advanced homework. Regular homework was class prep. Advanced homework is application and extension of basic skills that don't go quite to the level of proofwriting. These are higher complexity than just basic skills, but lower complexity than writing mathematical proofs. Mostly real-life applications, and there are plenty of them in this particular class, so it was real easy to make these up. These were given roughly weekly. Sometimes we skipped a week or it was 10 days in between, but I believe there were 7 of them, eight of them overall. Actually 9, I can't take that back. And these are graded success or retry on the basis of completeness, effort, and whether or not the work was overall mostly correct. I would look the other way if there was some 1 or 2 errors in the work. Didn't have to be perfect, as long as there weren't too many or too major of error. I call that a successful attempt at an application extension. It is possible to get a retry if you don't meet the standards for success, and if that's the case, you get 1 reattempt on the homework set. Usually do 1 week later, 1 week after I return the work, I should say. You get the feedback from me, and then you got a week to make corrections, and then that's your reattempt. Unlike proof problems, which you could just reattempt 3 times a week forever until the end of the semester. Where this all fits together on Bloom's taxonomy, I tried to create a wide spread that covered the entire scope of Bloom's taxonomy. The proof problems really hit at the uppermost level where there's a lot of creativity and evaluation involved. The advanced homework was kind of in this green area here. In fact, I initially was calling this application analysis homework, but that was a little bit too much of a mouthful, so I just call it advanced homework. Skill exams were kind of on this lower level, and the homework was way down here at the bottom. Really important, but on the bottom. I'm just asking students to do the basic entry-level tasks for new concepts, not the advanced stuff. Okay, we want to focus on the middle 1/3 of Bloom's taxonomy in the class meeting, if at all possible. So that's how this all fit together. There's one other item that I mentioned earlier that I haven't talked about that figures into the grading system, and that is engagement. Now, engagement for me means anything that sort of represents doing your job as a student or contributing to the learning community of the class. And this can mean a lot of different things. I assess these with what I call engagement credits. These are basically points. I should just say points probably, but I don't like to use points, and I'm sort of on this warpath against points. But anyway, engagement credits were points that I awarded for doing stuff that represents engagement. For example, attending a class meeting earns you 1 engagement credit. There was a whole suite of startup activities in week 1 that led students through the syllabus, through the grading system, a personal information survey, and a few other things as well. That was worth 20 engagement credits. That was a big chunk. Other things included filling out feedback surveys. I would give engagement credits for that. We had a guest lecture once or twice that was interesting, so I gave engagement credits. Not extra credit like you might think, because there's no credit. There's nothing, so therefore no extra credit. But engagement, yeah, that's a form of engagement in the class. And a lot of other options as well. So if you're a student, for example, that has a personal situation that makes it hard to attend a guest lecture, that's okay. There are plenty of other things you can do to earn engagement credits. These all just go into one giant basket of points called engagement credits. Now again, you could ask this question, should engagement even be assessed, or is that a form of inequity? Speaking of, for example, the student that is in a personal situation that makes it hard to do things like attend a guest lecture. In my view, I really want students to be engaged in the class, and so I'm going to assess it. And if I'm going to do that, I really want to assess it. If I'm going to do that in a way that's helpful for all students, I just have to give lots and lots of options, and I did. And so that's my take on that particular question. Now, we come to the point of determining how does all this stuff come together in the end to determine a course grade. Well, I'm glad you asked. Here is how it works from the syllabus. It's not a formula, but a big table that includes thresholds of accomplishment for all of the moving parts that you just saw. Now, for reference, we had 14 skills. I believe we had 9 advanced homework assignments. There were 10 proof problems. I believe we ended up with like 27 homework sets when it was all over with, and close to 100 engagement credits before it was all over with. And the way this works is to simply, if you want to earn a grade, you complete all the requirements for the row that has that grade in it. For example, if you want to earn a B in the class, you must master 10 skills, eventually earn 4 successes out of 9 on advanced homework, do 2 successful proof problems or more, complete at least 16 homework problem sets successfully, and earn at least 50 engagement credits. That's the threshold. The base grade that you earn in the course, and by that I mean A, B, C, D, or F without plus or minus modifiers, the base letter grade is the highest grade for which all the requirements are met. So for example, if a student masters 13 skills but only has success on 4 homework assignments and only 2 proof problems and only 16 homework sets and only 50 engagement credits, the highest row that they've met all the requirements for is a B, even though they exceeded that in one place. So it's the highest grade for which all requirements are met. Now, you might be wondering some things at this point, like what happens if a student has all 14 skills mastered but only has 2 advanced homework sets with successful on? Do those sort of like average out in the middle to be a B? The answer is no. The categories here are discrete from each other. They are kind of orthogonal to each other in many ways. They don't cancel out. One doesn't replace another. One does not average together with another. Remember, the grade of A means consistent excellence across the board. And so it's not a feature of this grading system to have like a very low level of skill mastery that is somehow made up for by having very high levels of something else. Skills are different, and they're different from doing proof problems, and I can't infer that a student has mastered basic computational skills by looking at their proofs. I just can't. They do not mix with each other. A grade of F, by the way, is given if you do not meet all of the very minimal requirements for a D. Now, going back to the mixed case here, I will say that in borderline cases, for example, if a student had like everything satisfied for an A except for homework, something that's really, really close, what I would do is look at the student's entire scope of work and especially focus on homework and engagement credits. Okay, was the student putting in the effort on the day-to-day simple stuff? If they were, then I'm going to look favorably on their borderline case. If not, I'm probably not going to look favorably on their borderline case, and I'll make a judgment call in the end. And I will make a note of that judgment call so that I make the same judgment call for another student who might be in the same position. This other bullet point that was before that also mentions a caveat in the grading system that says if you don't master all 5 core skills at least once, then there's a 1-letter grade penalty that's incurred. So speaking of plus and minus grades and the final exam, I haven't mentioned the final exam yet. We did have a final exam, and it was simply one last skill exam attempt. It was one more skill exam with all 14 skills represented. Now, you can come into that final exam either having mastered all of the core or not. Okay, every student is expected to attempt at least the core skills. For some of these students, it might be they haven't passed the core, they haven't mastered the core skills yet, so this is like their last chance. But for others, for most others, they had mastered all 5 of the core skills, and this is just going to be a reattempt for them. The way that the final exam contributes to the course grade is through plus and minus modifiers. You will earn a plus on your base grade if you master the core skills, all 5 of them, a second time on the final, plus master any 2 others. So this is another attempt to show mastery level work on at least half the skills, including all 5 of the core. And you earn a minus if you do not master the core a second time on the final. This could be because you mastered it once before the final, mastered all 5 of those skills once before the final, but came into the final and it didn't work out. Or it could be because you did not master all 5 of those skills before the final, and so this is just your first time doing it on the final exam. Or if you just don't even take the final exam. If you don't do either of those 2 things, which is possible, for example, you master all 5 core skills but don't do anything else, then you just keep whatever grade, plain letter grade, you walked in with. And so the final exam is a chance to give one more layer of triangulation on your skill mastery. And that's the only thing it did. That's the only impact the final exam had on the grade, was plus minus. Okay, so I don't know if you absorbed all of that. I told you it was a lot of weeds, and this is why I didn't go into it in the main keynote. This video is already nearly an hour long, and I only had an hour for the main keynote. So this was the weeds. So let me just kind of end here by unpacking what I liked about this system and what I didn't, and what I'm going to change, what I currently have changed. So what was good about this system was, first of all, it truly represents all 4 of the 4 pillars. We had clearly defined standards, we had helpful feedback, marks that indicate progress, and reattempts without penalty. So this is firing on all cylinders literally all cylinders of the 4 pillars. Especially helpful, the reattempts without penalty really lowered the stress, particularly when it came to the writing aspects of the course, like proofwriting. Proofwriting is incredibly stressful for students. They've never done it before. They've written a lot of code, but never any words to describe why the code works. And so the only way really to learn how to write a proof is just to attempt to write a proof and get feedback on what happened and try again. You can hear lectures about proofwriting all day long, but honestly, they just don't do any good. You just got to sort of butt your head into an actual proof problem and give it a shot. And so this gave students sort of a risk-free way to do that, and that was really good. I used to do skill exams in past courses similarly to what I described here, but on a much more frequent basis, like every 2 weeks, or in one case every week we did this. That became a real grind after a while, and students felt like nothing was happening to them except being assessed and quizzed constantly. The culture of the class became one of constant assessment. And so that's why I dialed this back to every 3 to 4 weeks. And I think that's the right cadence. It's not too frequent, it's not too infrequent. Students found, surprisingly to me, the students found the homework, the prep for class, to be very useful, and had very high completion rates on that every single time I assigned them. I figured they would really hate this because it's like students don't like thinking that they have to teach themselves things. But my students really enjoyed that, especially when they had the guidance, and they found it to be really useful in getting right to the hard stuff when we got to class. And I felt like this course was an appropriate level of challenge for students. The students who were a little bit like not superstar students were appropriately challenged and had plenty of opportunities to earn a good grade in the class through appropriate levels of work. And the really high-performing students could select even higher challenges if they want to. I didn't have a single student say that they were bored with the work in the class. But it wasn't all sunshine. There were a lot of things that I didn't care for once this was over with. I bet you can guess some of these. The plus-minus policy, starting at the end of this presentation, the plus-minus policy that I described at the final exam was just really, really confusing, and it happened at the worst possible moment, which is at the end of the semester, and I am not doing it that way again. I like the idea of having a final exam whose only impact on the grade is to determine plus-minus modifiers, but I tried to do too much with that final exam, and it just got to be very, very confusing. So I showed you the details, but just be warned that I'm not doing those details ever again, because it was not a happy ending to the semester in some cases. There really wasn't enough class time practicing on working with proof, either writing or evaluating proofs. I would give demos of proofs through lecture in class, and I should have known that lecture just really does nothing to move the needle on student understanding of hard conceptual tasks. I think we all know this, the research points to it, but I just figured if I show students enough well-done proofs, they'll just sort of get it, and it didn't happen. So that was a case of misalignment between my clearly defined standards and the activities that we did in class and the assessments that were given over those activities. The assessments align pretty well with the standards, but the class activities are out of whack. So the next time I teach the class, I need to do a much better job of giving students practice with thinking about what a good, correct proof looks like and how to build one. I will have to admit that I had serious problems, and I mean serious problems, with generative AI academic dishonesty on anything that was done outside of class. That was proof problems and advanced homework. I have written on the Grading for Growth blog about this, and I don't blame this. I'm not pointing fingers at students. I'm just saying generative AI is a thing that is out there, and it's having a major impact on students' work. Especially, I mentioned at the beginning of this talk that this class is not a prerequisite for anything else in a student's computer science curriculum. And so there can be the temptation for a student who is a junior or a senior, a third or fourth year student, taking this class, and also, therefore, taking some very hard, high-level computer science classes or engineering classes at the same time. If they're given a proof problem to do and they don't have any idea how to do it, it's going to be hard. And the class itself doesn't plug into any other classes to just, offload the work of a proof problem into ChatGPT and let it do it. I'm not saying many students did this. Some did, I will have to admit. I actually have no idea how many did, because ChatGPT's responses are essentially human at this point. I just know that I have a great sense that this was much more prevalent than I think it was on proof problems and advanced homework. And this is an ongoing issue that all of us in higher ed are going to have to grapple with. And I'm still trying to find answers for that as of this moment, which is January 21st. I will try to check back in later. Probably my whole system was just way too complicated by about one or two too many assessment categories. Like, I might have been able to just completely remove advanced homework. I bet I could have done that, and it would have been just as good as anything else. In fact, in my current class, which is the first semester, I'm teaching it now in January of 2025. It's the first semester of this two-semester sequence, and I only have 3 categories, which is skills, some advanced problems that are assessed through other kinds of exams, and engagement. And so this is like a 3-tiered system that is just much, much simpler and easier to navigate. One of the things you can do for yourself when creating an alternative grading system is just be really, really careful not to try to do everything that comes to mind that seems like a good idea. You can only do so much as a human being before you end up completely underwater with grading because you gave 10 essays when you could have gotten by with 5 or something like that, or no essays in some cases. So always think twice about whether you really and truly need to have an assessment type in your class. Like my advanced homework, again, I probably could have just completely eliminated that, and it wouldn't have lost much in the system. Or at least dialing back the number of things that you do assign in each category, so it's like at a reasonable level. So in conclusion, I hope this was useful for you, and I applaud you if you sat through and listened to all of this stuff, because that was pretty much in the weeds. This is my entire line of thinking, and I can do more videos like this if people want. That gives you the full scope of what it's like to conceive of implement, and then run, and then do a post-mortem on an alternative grading system in a class. My system's not perfect, as I hope I have made very, very clear, and this is just one person doing one class, okay? So your class, your students, your situation, your style of doing things could be completely different from mine, and that's okay. I would encourage you to check in with the Grading for Growth book, which has 17 different case studies in it of alternative grading systems, similar to what you've just seen in this video, from a variety of institutional types and course sizes and course modalities and institution and disciplines and so on, to get a really broad spectrum of what's out there. And also check in with the Grading for Growth Substack, which is gradingforgrowth.com. And every month we are publishing 2 guest author articles, and many of those are implementation details of what they're doing in their classes. Between all this and also your colleagues, of course, maybe people you were sitting next to or in a Zoom box next to at your own institution are just as interested as you are in this stuff. So connect with them, get their email, get their phone number, and see if you can work something out to try something, maybe as a faculty learning community at your institution. I wish you the best, and I hope that this was helpful to you. And again, please reach out to me on social media or give me an email if you have any questions about anything. Thanks again.